Urban mobility data is the backbone of modern smart city research, from traffic optimization to location-based services. But there's a fundamental bottleneck. Privacy regulations and the high cost of real-world data collection make large-scale, high-quality trajectory datasets incredibly scarce. Researchers need synthetic data to train models and validate algorithms, but existing generative approaches fall short. Most methods treat trajectory generation as a direct mapping from Gaussian noise to raw GPS coordinates. They operate purely at the micro-level, which means they completely miss macro-level travel patterns like congestion clusters, acceleration zones, or deceleration segments. They're also locked into fixed sequence lengths, and they only support rigid limited conditioning, usually just start and end coordinates. To solve this, we need a framework that respects the hierarchical nature of human movement. That's exactly what HTP delivers. Instead of brute-forcing GPS point generation, HTP flips the pipeline. It generates macro-level travel patterns, first using a large language model, and then reconstructs micro-level GPS trajectories from those patterns. This two-stage approach solves the precision, diversity, and conditioning problems all at once. Let's break down how the first stage works. We need to compress raw, variable-length GPS sequences into shared, semantic travel pattern tokens. We do this with a trajectory-specific residual quantization variational autoencoder, or RQ-VAE. The encoder takes normalized GPS coordinates and passes them through alternating one-dimensional CNN and transformer layers. These layers progressively downsample the sequence by a factor of 2-3 times. This compression is critical because it forces the model to learn segment-level spatial irregularities rather than getting lost in point-level noise. But variable-length sequences create a major architectural headache. When you downsample a sequence of 26 points, you get 13, then 7, then 4. If you naively upsample 4 back to 26, the math breaks because of odd-to-even length mismatches. HTP solves this by explicitly tracking the odd-even transformation during encoding. We record a binary mask of these transitions and feed it to the decoder, which uses conditional upsampling rules to perfectly reconstruct the original sequence length. Once the sequence is compressed, we apply multi-resolution residual quantization. Instead of a single quantization step, we use L layers. The first layer quantizes the input embedding. The second layer quantizes the residual error between the original embedding and the first layer's output. This repeats for all L layers. The final representation is a tuple of indices across all codebooks, which expands the representational space multiplicatively. By setting codebook sizes to grow across layers, like 32, 64, 128, and 256, we enforce a course-defined hierarchy. Shallow layers capture broad root semantics, while deeper layers refine them into fine-grained point density variations. Now, quantization inevitably loses spatial precision. If you try to reconstruct absolute GPS coordinates directly, the optimization becomes wildly unstable. GPS precision sits in the order of 10 to the negative 5th degrees, so tiny reconstruction errors cause massive spatial drift. HTP sidesteps this with a relative reconstruction loss. Instead of predicting absolute latitude and longitude, the decoder predicts two relative targets against the underlying road network. First, the relative percentage position of each point along its matched road segment. Second, a small spatial offset vector to account for GPS noise. This bounds the optimization landscape to a narrow, predictable range, making training stable and spatially grounded. That covers the compression stage. Now for the generation engine. We take these compressed travel pattern tokens and expand the LLM's vocabulary to include them, along with road segment tokens and length record tokens. We fine-tune the model using supervised fine-tuning on serialized question-answer pairs. The question is a natural language description of conditions: road sequence, start time, travel distance, sampling interval. The answer is the autoregressive sequence of travel pattern tokens. Because LLMs are inherently autoregressive, they naturally support variable length generation without architectural hacks. The model generates macro-level patterns under flexible text-based conditions, something diffusion and GAN models struggle with. Once the LLM outputs the token sequence, we unquantize it using the codebooks, aggregate the residuals, and pass it to the RQ-VAE decoder. The decoder uses cross-attention over road network embeddings to reconstruct the final micro-level trajectory. This means we can control generation through natural language, leverage the LLM's world knowledge for realistic routing, and still get precise, variable-length GPS coordinates. The results speak for themselves. Across real-world datasets, HTP outperforms the strongest diffusion and GAN baselines by nearly 30% on average. It captures realistic point density variations, maintains accurate road network alignment, and naturally matches real-world length distributions. You might wonder if adding an LLM introduces a massive computational bottleneck. It doesn't. The RQ-VAE compression reduces the token count by nearly 2 orders of magnitude compared to generating raw GPS points. Generating a typical trajectory requires roughly 8 tokens, instead of 15 to 20 times the original length. This keeps inference efficient, and ablation studies confirm that every component, the relative loss, the expanded vocabulary, the residual quantization, and the LLM backbone, contributes directly to the final quality. HTP represents a fundamental shift from brute force coordinate generation to semantic, hierarchical trajectory synthesis. By decoupling macro-pattern reasoning from micro-point reconstruction, it generates diverse, condition-aware trajectories that actually reflect how people move. If you're working on urban computing, mobility simulation, or generative AI for spatial data, this approach is worth exploring. The code is open source, and I'll leave a link in the description. Thanks for watching, and I'll see you in the next breakdown.